Hello students, welcome to Marine Engineering Tutorials. I'm Atul Kumar Gupta and I'm back with a new tutorial. Presently we are studying marine auxiliary systems. We will first learn about the layout of equipment on upper and A deck level in the engine casing. Then we will explore the layout of equipment at B and C deck level in the engine casing. Finally, we will examine various propulsion systems used on ships with their specific features. Let us now go through each of these topics one by one in the following slides. Layout of machinery in engine casing at upper and A deck. This sketch shows the equipment located in the engine casing on the upper deck and A deck levels. Two auxiliary boilers 1 extend up to the upper deck. The main engine exhaust pipe 2 coming from the turbocharger outlet passes through both the upper deck and A deck. Three generator engine exhaust pipes 3 originating from the second deck extend upward through A deck and upper deck within the engine casing. The incinerator exhaust fan 4 located on the upper deck maintains a slight vacuum in the furnace to prevent blowback and discharges the exhaust gases to the atmosphere. The waste oil settling tank 5 located on the upper deck receives sludge and waste oils for the incinerator. Settled water is drained off. The stern tube lubricating oil gravity tank 6 maintains static oil pressure in the stern tube to counteract the external seawater pressure. Typically, two gravity tanks are used on tankers and bulk carriers, one for loaded draft and the one for ballast draft. Two boiler, two pipes, 7 carry exhaust gases from the A deck. Two boiler forced draft fans 8 located on the A deck supply hot combustion air to each boiler. The freshwater expansion tank 9 located on A deck compensates for thermal expansion and contraction in the diesel engine, high temperature and low temperature cooling water systems. It maintains the water level within specified limits and is equipped with high and low level alarms, a filling valve, a drain valve, and an overflow pipe. It has an inspection cover through which chemical can be dosed to maintain the required alkalinity. The inert gas system scrubber unit 10 located on the A deck washes the boiler exhaust gas to cool and clean it before supplying it to the cargo tanks, creating an inert atmosphere to prevent explosion. Two inert gas fans 11 located on the A deck draw boiler flue gases through the scrubber and deliver them to the cargo tanks. The oxygen analyzer 12 located on the A deck continuously monitors the oxygen content in the inert gas supplied by the IG fan. It triggers an alarm if the oxygen content exceeds 5% and vents the inert gas to the atmosphere until the oxygen content falls below 5%. Purifier room fan exhaust pipe passes through upper and A decks. Insulator exhaust pipe passes through A deck. Layout of machinery in engine casing at B and C deck. The sketch shows the machinery layout in the engine casing at B deck and C deck levels. The main engine exhaust gas boiler 1 located on the B deck also extends to C deck. It recovers waste heat from engine exhaust gases to produce steam while ship is underway before the gases exit through the funnel. Two auxiliary boilers, two pipes, 2 pass through the B deck and C deck before discharging through the funnel. 3 auxiliary engine exhaust pipes 3 pass through B deck and C deck before exiting via the funnel. 4 ventilation fan 4 located on the B deck supply ventilation air to the engine room. One of these fans is reversible and operates in exhaust mode to ventilate the engine room after a major fire has been extinguished using CO2 flooding. Purifier room exhaust pipe 5 leads the exhaust air on this deck. Incinerator exhaust pipe 6 passes through this deck and goes to the funnel. Various ship propulsion systems. Ships use different propulsion systems to convert engine power into thrust to move the vessel through water. The choice of propulsion system depends on ship size, speed requirement, fuel efficiency, and operational purpose. Various propulsion systems used on ships are discussed here. Steam turbine propulsion. In this system, steam produced in boilers drive the turbine connected to the propeller shaft. This was used on earlier merchant ships, which is on the decline, and now it is restricted to naval ships only. It provides smooth operation with low vibrations and can use different fuels. It has lower efficiency than diesel engines and require large boiler plant. Diesel engine propulsion system. This is the most widely used propulsion system in modern merchant ships. Usually a slow speed reversible marine diesel engine directly drive the propeller shaft, which is used for large cargo ships. Alternately, a unidirectional medium speed engine with controllable pitch propeller or reversible engine with gearbox provides propulsion for ferries, cargo ships, and offshore vessels. Diesel engine propulsion system provides higher thermal efficiency, low fuel consumption, and is reliable for long voyages. As it is a heavy machinery, it causes high noise and vibrations. Gas turbine propulsion. A gas turbine is similar to aircraft engine in which air is compressed, fuel is injected and burned, high temperature gases expand through turbine blades producing power. These are used for high speed vessels and naval ships such as destroyers and frigates. They have very high power to weight ratio and start and accelerate quickly. They have high fuel consumption and maintenance is expensive. Diesel electric propulsion. In this system, diesel engines drive generators, electric motors drive propellers. To reduce the size of motors, high voltage at 6.5 volt is used. This system is used for cruise ships, icebreakers, research, and offshore vessels. This system offers flexibility of machinery layout, good maneuverability, and reduced vibration. Although they have disadvantages such as higher installation cost and electrical power conversion losses. Nuclear propulsion. This system is mainly used in naval ships such as submarines and aircraft carriers. It uses a nuclear reactor to generate heat through nuclear fission. The generated heat produces steam which drives turbine to turn the propeller. It has extremely long endurance without refueling and provides higher power output. Its cost is very high and poses safety concerns due to radiation. Podded propulsion. This is an electric propulsion system where the motor is inside a rotating pod outside the ship which drives the propeller. The pod can rotate through 360-degree, providing both propulsion and steering. It provides improved efficiency and excellent maneuverability without rudder. This system is suitable for cruise ships, icebreakers, and ferries. Water jet propulsion. In this system, propeller is replaced by a water jet. The water enters through the pump which accelerates the water and high speed jet exits through a nozzle creating the thrust. This system is used for fast ferries, patrol boats, and high speed crafts. It offers high speed capability, good maneuverability, and safe operation in shallow water, although it is less efficient at lower speeds. This completes our study of equipment located in the engine casing on various decks and types of propulsion used on the various types of ships with their specific features. This book has been written by me and covers all the topics as per the Indian Maritime University syllabus. It explains key concepts using simple illustrations. The book also includes answers to all questions that have appeared in examinations conducted by Indian Maritime University. I am sure that the book will help students prepare effectively for exams and also support them in working safely with marine auxiliary systems. I hope you enjoyed the lecture. Feel free to share your feedback in the comment section. If you found the tutorial helpful, consider sharing it with your friends. Subscribe to the channel to stay updated with upcoming tutorials. I'll be back soon with a new lecture. Thank you for watching till the end.